between steps are given. So the steps are like this. I will write the number, how many threads are there in a flight. I am drawing here randomly. So for the understanding purpose, I am drawing here randomly. And now these are also steps. Okay. So here the steps in this flight. Okay. So in this flight there are 10 threads. Okay. Here also how many threads? 10 threads. So total it becomes 20. And here 5 threads are here at this point. Okay. So this is the given diagram to you, and the dimensions are also given. So if I write the dimension, then this length is 2800, so it is 2.8 meter. The point I will show over here from this end to this landing. This is 2.8 meter. Then next is, this is 1.4 meter. 1.4 meter is, this landing is of 1.4 meter, and this remaining now, whatever remaining is there, this much. Okay, so this is 300. What is the width of support? Is it given in the problem, or it is given in the diagram only? You can assume it as 230, 300 mm, up to 450 mm you can assume, if it is not given, and if it is given then let me know in the chat. Okay. So in the similar way, if you see this side, so now I will quickly draw the arrows first from this point, the distance, again from here, okay, and then from this point also. So that for this landing, sorry, for this landing, it is again, this is 1.4 meter. Okay. Then this in between length, it is also 1.4 meter, and this is also 1.4 meter, and this width, this is again 0.3, this is again 0.3. Okay. This side also, this width is 0.3, which I have not shown over here. So now based on this we will find out the effective length. Okay, here there is no need to finalize the riser and thread, because already the number of steps are given to you. Okay, they have already told you there are 10 threads in this flight. Okay, 10, they have already told you 10 threads in this flight. Okay, then 10 threads in this above flight. Okay, and here there are 5 threads. Also they have given you the dimensions of the landings also, and the dimensions of the supporting wall. And here at the approach we always put the beam here. Okay, because the load of the open well staircase is slightly high. So these are the given things. Now we will move to the, first I will give the names. Okay, let us consider this as A, this is B, then this is C, and this last point is D. Okay, so effective lengths of AB वॉल थिकनेस दिलंय का 230 mm? कधी सांगणार तुम्ही? मगापासून मी विचारतोय. So it is not 0.3, it is 2.23. Okay, so it is 0.23. It is given in the problem. Okay, problem मध्ये दिलं नसेल तर तुम्ही assume करू शकता. You can assume if it is not given in the problem, but now it is given in the problem, so we will take that value 0.23 meter. Okay, so now based on this is the diagram. So we will find out the effective length AB, then BC, whatever may be the dimensions of AB, whatever is the effective length of AB, same is the effective length for CD. So I will write here now flight AB, which must be equal to CD, which is equal to, we want to find out the effective length. Okay, so the effective length in this case is the center to center distance of the support. Okay, so if we want to find out the effective length, then that effective length will be, if I draw here a line, okay, this is the center line, this is also the center line, and this center to center distance, this distance which is center to center, is nothing but the, this center to center distance is nothing but your effective length. Okay, so this is your, this is your effective length, or I will write here L effective. So now for that, see, we start from this point. Now this is point 23. Okay, this is point 23. So point 23 means what? It is point 23 divided by 2, half of the support. Okay, as we are taking from center to center, then it is 1.4. So plus 1.4 plus, then again it is 2.8. So it is 2.8 plus again this much of distance, हे जे काय राहिला असेल हे half. So total support is 230. So it is again 230 by 2. So it is 0.23 by. So let me know the answer. It is 4.43. Okay. So this is 4.43 meter. So these are the effective spans of AB and CD. Okay. As AB and CD are equal, the bending moment in both the flights are equal, and the steel which we are going to provide for these two flights AB and CD, it is also equal. Now we come to this point BC. Okay. Now think about BC. We will calculate the effective length of BC. Okay. So flight BC, flight BC, which is equal to, so flight effective length of flight BC is equal to, now again it is nothing but the center to center distance. Okay, from this point, okay, this is the center, from this point up to the center of this. Okay, this total distance is nothing but the effective span of BC. So I will write here directly. If you won't understand, then let me know. So I will repeat. So here it is again 0.23 by 2, half of this support, plus this vertical distance 1.4, again plus 1.4, again plus 1.4, plus 0.23 by 2. So you will get the effective length. BC is also same 4.43. So it is again 4.43 meter. So these are the effective lengths of AB and BC which we have calculated. Now we will move to the depth of the slab. So the next thing is depth of the slab. Depth of west slab. Okay. So depth of the slab we need to calculate. So we will do our assumption. What we assume normally? Assume assume 40 mm depth. Okay, 40 depth per meter span. So it means that your overall depth D is equal to 40 into 4.43, 177.2. Okay, so it is 177, 177.2 mm. So we round this depth. Okay, so we round this depth to 190 mm. Okay, let us keep on safer side, because if it fails then we have to again do all the calculations. So instead of 180, I am keeping it for 190 mm. Okay, so now this is our depth. If you take here 180, then also there is no problem. Okay, if you take here 180 and your check for depth is satisfied, then there is no problem. You can take any value over here, but it must be greater than this 177.2. So now next is the loading. Okay. So load calculations. Load calculations. Now in the load calculation, first thing is the that weight of slab. Okay. Weight of slab. So how do we calculate the weight of slab per meter, weight per meter run? So it can be calculated as its overall depth. So what is the overall depth we are considering over here? 190. So it is 0.19. Okay, 0.19. Now I will write here directly into 25 into this slab is inclined, due to which we are taking into the account one factor, that is under root r square plus t square divided by t. Okay, so r square plus t square divided by t. In the numerical they have told you that staircase with open well is having step size 280 by 150 Okay, so it is given in the problem. So it is 0.15 square plus 0.28 square whole divided by how much it is? 0.28. So if you solve this, you will get the weight. It is 5.39. Okay, it's 5.39 kilonewton per meter. After that, weight of steps. Weight of steps. How do we calculate the weight of steps? It is r by 2 into 25. So it is half into your riser is 0.15 into 25 into 1 is also there. So let me know the answer of this. Answer is 1.875 kilonewton per meter. So these are the dead loads. Okay. So total dead load we will calculate now. So total dead load is equal to 5.39 plus 5.39 plus 1.875 plus 1. Kavita Parse, switch off your mic. So the answer is, what is the total dead load? So it is 8.265. Okay, so it is 8.265 kilonewton per meter. So this is total dead load. Now we will take live load. So live load is equal to how much it is given in the problem. Live load 3 kilonewton per meter square. Okay, so it is 3 into 1, which is equal to again 3 kilonewton per meter. Okay, this is your live load. Then calculate the total load, that is dead load plus live load. Okay. So total load is equal to, it is dead load plus live load, which is equal to 8.265 plus 3. So it is 8.265 plus 3. How much it is? 11.265. 11.265 kilonewton per meter. Okay. So this is the total dead load, total load. Now calculate factored load. Factored load. So this is your W. Total load is nothing but your W, and factored load is WU. That is ultimate load or factored load. So it is 1.5 into 11.265. What is the answer? There is 16.89. Okay, 16.89 kilonewton per meter. So now after this we will calculate. This is the load on flight. Okay. Now we will calculate what is the load on landing. Okay. So load on landing slab. So in that first thing is there weight of slab. Weight of slab. So the weight of slab is its overall depth 0.19 into 25 into 1 is there 4.75 kilonewton per meter. This is the weight of slab. Then floor finish. On landing the steps are not there, so weight of steps here you should not consider. It is 1 into 1, which is equal to 1 kilonewton per meter. And after that live load. Live load is 3 kilonewton, 3 into 1, which is equal to 3 kilonewton per meter. So add the load and let me know the total load. Ah, so what is the total load? Total load is equal to, so it is 8.75. Okay, 8.75 kilonewton per meter. So this is our total load. So calculate the ultimate load now, that is factored load. So ultimate load is equal to 1.5 into 8.75. Let me know the answer. पुढचं कॅल्क्युलेट करून ठेवलं नाही का एवढ्या वेळात. So 1.5 into 8.75 fast. It is 13.125. This is 13.125 kilonewton per meter. Okay. So this is our ultimate load on landing slab. So now you got the load on the flight, okay, as well as you know the load on the landing. Now our next job is to calculate the bending moment. After calculating the bending moment, we will take the check for depth. So next thing is bending moment calculation. So bending moment. Next is the bending moment. So now to draw the bending moment diagram. Okay. So here the bending moment of, if you observe, see the geometry now here in this case. Now if you see for AB flight from point A up to this point, okay, here is the load on flight which we have calculated, and there is a landing after that. Same is the case for flight CD. Okay, here is the load on the flight, one flight is there, one landing is there. But we observe flight BC. So here flight load is there and also the landing is there at both the sides. Landing is there on both the sides. Here for AB and CD, landing is there on only one side. Okay. So now that is the difference. So we are going to calculate the bending moment for flight AB, flight CD, and what is the bending moment for flight BC. So that we are going to calculate over here. So for that now, so bending moment. So first I will consider flight AB and flight CD. Okay, so bending moment, here I will write for flight AB and CD. For that we need to draw the diagram. Okay, so I will draw the diagram over here. This is flight, and now support. This is the support. Now what is the distance? You need to find out the distance. Okay, so see for flight AB, what is the effective span of flight AB? What is the span? If you see, this is the effective span. This is from D point to C point. This is the effective span for both the flights CD and AB. Okay, 4.43, correct. That is the effective span. म्हणजे या इथं जे तुम्ही सेंटर घेतलंय ना, इथं हा एक सपोर्ट असणार आहे आणि इथं एक सपोर्ट असणार आहे. Okay, at the center, because we are considering the center to center span, so we will take the position of the support at the center over here. Okay, so this mid length is 2.8 meter plus 1.4. So how much it is? 2.8 plus 1.4. 2.8 plus 1.4. How much it is? 4.2. Okay, so the 4.2 is the distance. So if I show you from this point up to here, C point, this total distance is 4.2. See, from this point to this point up to 2.8 plus 1.4. So this total is 4.2. But this is not our distance 4.2. What we want? Further distance. So further is, if this total support is 0.23, then this will be 0.23 by 2. Okay. So 0.23 by 2 येणार आहे एवढं distance उरलेलं. This is 0.23 by 2. This remaining distance is 0.23 by 2. So from this point, the distance will be 1.4 plus 0.23 by 2. Okay, and here on this side for 2.8 meter, support is over here. So what is the distance again? 2.8 plus 0.23 by 2. So how much it is? 2.8 plus 0.23 by 2 plus 0.23 by 2. It is 2.915. So 2.92. It is 2.92. So if I go back here, from this point I will take a distance up to over here, suppose up to this point. This is 2.92 meters. So up to this point UDL is there, which is having higher magnitude. Flight वरती act होणारा UDL असणार आहे इथं. This is the UDL. Okay, and on the remaining portion again UDL is there, but it is on the landing. Landing UDL will be there, which is acting on the landing. So what are the values now? For landing 13.125 and for flight it is 16.89. So here it is 16.89 kilonewton per meter, and here it is 13.125 kilonewton per meter, and this remaining length, okay, so this remaining length, how much it is? It is 1.4 plus 0.23 by 2 by 2. It is 1.515. Okay. So this length is 1.515. So I will write here 51 meter. Okay. So this total becomes 4.43. So this is our loading diagram now. Okay, so again we need to draw the diagram. I will draw the diagram quickly now. So here is the beam, then the supports are provided. These are the supports which are provided. Then the next thing is the distances and the UDL. So from this point at a distance of round about 2.92 meter, your flight load is there, and from this end, that is from the remaining point, here it is 1.92. So I will write the values. This is 1.51 meter. Here it is 2.92 meter, and then we will show the UDL. Here it is the UDL, that is our flight load, and after that this UDL which is on landing slab. So this UDL which is on the landing slab, it is 13 point how much 125, no? If I take any wrong value, let me know in the chat box, huh? And what is the load over here? It is how much? 16 point something. I forgot. 16.35. What was the load? 16.89. Okay. So it is 16.89 kilonewton per meter. So now if you see these points, then here it is your reaction RA. Suppose now this is your point A, this is your point B, this is the reaction RB. Now we need to find out the maximum bending moment over here. Okay, so to calculate the maximum bending moment, first calculate the values of reactions. So we will calculate the value of RA just. Okay, so we will take sum of moment of all the forces about B equal to 0. All clockwise moments are positive as we are calculating the reactions, or anti-clockwise moments are negative. So what is the distance of RA then? It is 4.43 RA. Okay, it is moving in clockwise direction, so this is plus. Moving in clockwise direction, so this is plus. Then this UDL minus, so first convert that UDL into the point load. it is 16.89 into 2.92. So this is the conversion of UDL into the point load, and multiply by the distance. So now we are taking the moment at point B. So from point B we need to calculate the distance of this. So this UDL, if you convert into the point load, it will act at the center. So it will act at the center of 2.92. So what is the center of 2.92? 2.92 divided by 2, it is 1.46. So from half of the at the midway this will act. So this distance is 1.46 and plus 1.51. 1.51. So what is the answer? What is the length then? It is round about 2.97. Please check. So this is your distance. Okay. Again minus. Still, if anybody is having any difficulty in this conversion of UDL into the point load and taking the moment, then please let me know in the chat box. So I will explain you once again. This is very important thing. Every now and then you need this. So is it right? 2.97. So 13 point next UDL, 13.125. What is the span of the UDL? It is 1.51. So multiply it by 1.51. So this is the conversion of UDL into the point load, and that load will act at the center of 1.51. Okay, at this center that load will act. So what is the distance from point B? So distance from point B will be 1.51 divided by 2. So 1.51 divided by 2. How much it is approximately? I think 0.75. Okay, it is 0.75. It is 0.75. Okay, this UDL is also over. And then what is the moment of RB? It is 0. So if you solve this, you will get the value of RA. Let me know the answer. 36.44. Okay. So RA is 36.44 kilonewton. As we got positive answer, it is moving up. Okay. So now we need to find out the maximum bending moment. Now how to find out that maximum bending moment? Anybody? How to find the maximum bending moment? What is the relation between shear force and bending moment? Hmm? What is the relation between shear force and bending moment? So when you will get the maximum bending moment, at what point your bending moment is maximum? At which point? At which point it is maximum? So I am asking you the basic questions. So to find out the maximum bending moment, see, point of contraflexure is the point where the bending moment is 0. Okay, so we don't want that point. We want a point where the bending moment is maximum, and we want to find out the maximum bending moment. Now if you observe this beam, if you observe this is not a symmetrical loading section. जर जे तुम्हाला मागच्या वेळेस मिळत होतं सिमेट्रिक लोडिंग वगैरे असायचं. ओके, सेंटरला तुम्ही मॅक्सिमम बेंडिंग मोमेंट कॅल्क्युलेट करत होता. So now this is not the case. Okay, now the case is different. Now here we want to find out the point where the bending moment is maximum. So for the and the point of contraflexure is the point where bending moment is zero, not the maximum. Okay, and so what we will do now, here the bending moment is maximum maximum at a point at a point where where the shear force is zero. Okay, so when the shear force is zero, your bending moment is maximum. So now I will take a general section at a distance x and I will find out the equation of shear force. Okay, so now here SF at xx is equal to, so I will take one section line. Suppose now I have taken a section here at this point. This is my section line, and this section is at a distance x from this point. This section is at a distance x. X is the distance. So now if I want to calculate the shear force equation, shear force, if I want to calculate the shear force at this section, if I want to calculate the shear force at this section, then what should I do? I can either consider the right hand side equilibrium or I can go with the left hand side equilibrium. Okay, so we will go with left hand side equilibrium as we want to find out the point of zero shear first. So left hand side equilibrium, if you consider, then here is RA. First is the force RA, reaction or force. RA is moving upward, so it is positive. So 36.44. This is the value of RA as it is. Don't multiply it by any distance because we are calculating the shear force, not the bending moment yet. Okay. Then this UDL. Next is you think about this UDL. Now what is the span of this UDL? The span is X. This is the length of UDL. This length is X. Its magnitude is 16.89. Okay. So the shear force is, now the shear force is, this UDL is moving down, so it is minus 16.89 into X. That is 16.89 into X. This is the shear force at general section. Okay, this is the shear force at general section at a distance X. At a distance X. But where do we get the maximum bending moment? At a point where the shear force is 0. So if we equate this equation to 0, then we will get the point where the bending moment is maximum. Okay, so therefore here I will write the equation 36.44 minus 16.89x, 36.44 minus 16.89x must be equal to 0. So therefore x is equal to, now what is the value of x? It is 2.16 meter from, कुठून calculate केली आपण value, from which point? From point A. It is calculated from point A because we have measured x from point A. So from point A. Okay. So now we are going to calculate the bending moment which is maximum at, so I will again mark the distance. So this total is 2.92. So 2.16 may be somewhere here up to this point. Okay. So up to this point, this distance is, this is 2.16 meter somewhere here. And now again we will consider the section over at this point, or if you consider the point, if you project this somewhere here, the point will be there. here is the point where the bending moment is maximum. Let us assume that this is point E. I will call this point as point E, or either you can take the section over here also. Okay, so I will call that point as point E. Now I will calculate the bending moment. So bending moment bending moment at point E is equal to. So now if I consider the left hand side equilibrium, then how many forces are there? I will remove this section for your understanding. Okay, I will remove this X also. We can consider right hand side equilibrium or left hand side equilibrium. So we will go for left hand side equilibrium. So from point E, what is the distance of RA? It is 2.16. Here it is given 2.16. Just now we have calculated 2.16 meter. So the moment of RA is moving upward. So what was the value of RA? RA is 36.44. So it is 36.44 into 2.16. This is moving up, so plus. The next term will be minus because UDL is there and it is moving down. UDL is there and it is moving down. But see here, you should not consider the span of the UDL as 2.92 because our point is here and we are considering the left hand side equilibrium. So whatever UDL is present on the left hand side of this point, that must be considered for the calculation. This UDL we are not going to consider for calculation. So on the left hand side, what is the length of the UDL now? It is again 2.16 meter. Okay, so convert this UDL into the point load and then take the moment. So it is how much? What was the value? 16.89. So 16.89 into 2.16. This is the conversion of UDL into the point load. Okay, conversion of UDL into the point load, and the distance is 2.16 divided by 2. So this is the distance. Okay, so this is the distance because it will act at the center of this 2.16. It will act at the center of this 2.16. So now the maximum bending moment is, it is how much? 39.31. Okay. So the maximum bending moment at E is काय राहिलं ना अजून 39.31. Check if any force is remaining or anything is there. So this is the maximum bending moment for flight AB and CD. Okay, so I will write here maximum bending moment for flights flights AB and CD is equal to 39.31 kilonewton meter. Okay, 39.34 kilonewton meter. Now similarly, we are going to find out what is the bending moment at flight BC. Okay, so I will give the heading again. Bending moment for flight BC. So again now we need to consider the BC flight. So here I will draw the diagram. This is the flight BC. Then supports are given. We will show the supports. These are the supports. Okay. Now again we need to see the distances. again we need to see the distances. Okay, so that diagram is right now not with me, but it is the center to center distance. You can see in the first diagram. What is the span? It is 4.43 meter. That is the total span. Okay, but at the center, now if you see at the center portion, which is of 1.4 meter, at the center portion 1.4 meter here, here is the flight load, and this load is 16.89 kilonewton per meter, and this distance is from this point it is 1.4 meter. Now again, what is the remaining distance? The remaining is 1.4 plus 0.23 by 2. It is again 1.51. Okay, 1.51, and this side also it is same 1.51. Okay, but the UDL is different. Here is the UDL which is acting on the landing. Is 13.125 kilonewton per meter. This is also 13.125 kilonewton per meter. Okay. Now we need to solve this. We need to calculate the maximum bending moment. You check it is matching with the total span or not. Okay. 4.42. So now what we will do, again here is the reaction. Suppose now this is your point B and this is point C. So here is now it is the reaction RB and here is the reaction RC. We are considering it for flight BC now. So now in this beam, first calculate the reaction RB, and now if you see this for a flight BC, it is symmetric. On both the sides landing is there, at the center this load is there. So the maximum bending moment will be at the center somewhere here. Let us say that this is point F. At point F, its maximum bending moment is there because beam is symmetric. And what is the distance of this point F? What is the distance of this point F? If we want to calculate the distance of this, what is the distance of this point? Okay, so the distance will be, if this total is 1.4, the center of 1.4 is 0.7. Okay, the center of 1.4 is 0.7 plus 1.51. So 1.51 plus 0.7. It is 2 point something will be there. How much it is 2.21. Okay. So this distance is 2.21 meter. So now calculate RB first. So to calculate RB, we will take the moment of all the forces above C equal to 0. So it is 4.43 into RB, it is clockwise, plus minus first UDL, how much it is 13.125, and what is the span 1.51. 13.125 into 1.51 into what is the lever arm? It will act at the center of this 1.51. So if it is acting at the center of 1.51, So what is the value? 3.665. 3.665. Next is next UDL 16.89 into 1.4. So 16.89 into 1.4. This will also act at the center. Okay, of this 1.4. So again, its distance from point C, it is the same 1.51 plus 0.7. It is 2.21. Okay. So again minus, it is moving down. Sorry, anti-clockwise. It is moving in anti-clockwise direction. 16.89 into 1.4 into, what is the lever arm? It is 2.21. Okay. Next, this UDL 13.125 into 1.51. So it is 1.51 by 2.755. So again minus 13.125 into 1.51 into, it is 0.775. 755. All these must be equal to 0. Let me know the value. Value channel. Okay. This is your RB. Now calculate the maximum bending moment. So bending moment at F. There is the moment is maximum. So it is RB into 2.21. It is moving up, so plus on this UDL 13.125 into 1.51. 13.125 into 1.51. This is the conversion of UDL into the point load, and then moment from point E. How much is the moment? It is 1.51 by 2. How much? 0.755. 1.455 is the distance. Then again minus, then again minus this much of UDL, remaining UDL. So it is 16.89 into 0.7. 16.89 into 0.7 into 0.7 by 2. So the maximum bending moment is, and the answer is, what is the answer? 36.78. Others, please check the value. So the next point is check for depth. Okay. Now to calculate this check for depth, first consider the maximum bending moment. This bending moment is 36.78 kilonewton meter. The previous maximum bending moment is it is 39.31 kilonewton meter. 39.31 is the greater value. Okay. So here I can write bending moment maximum is equal to maximum bend 39.31 kilonewton meter, equating bending moment maximum to moment of resistance or load carrying capacity. So it is 39.31 into 10 raised to 6 equal to it is 0.138 FCK d square. Therefore, D required is equal to calculate the answer. 111.94, 111.34 mm. ओके आपली इफेक्टिव डेप्थ किती आहे का आपण फक्त ओव्हरऑल डेप्थ काढली आहे ओव्हरऑल डेप्थ काढली आहे का फक्त हां so now effective depth first we need to find out what is our effective depth then only we can compare no so our overall depth overall depth D is equal to what is the overall depth it is 190 mm so effective depth small d is equal to 190 minus assume 15 mm clear cover and assume 10 mm bar diameter which we are going to use so 10 by 2 so it is 170 mm so this is safe okay. These two values are assumed these you mention it clearly you should write assuming you should write this assuming clear cover is equal to 15 mm and bar diameter is 10 mm that you should write the sentence assuming hmm, clear cover of this and this and bar diameter of this and this. I have skipped that step. I have written over here directly. Okay. So now if you see our D provided is greater than D required, hence it is safe. So here D provided is greater than D required, hence it is what it is safe. It is safe. Okay. So now this is the check for depth. Now after the check for depth is satisfied, then go for the steel calculation. Okay. So here I will use the heading steel calculations. Okay. So in that steel calculations first for flight AB and CD. So AST is equal to 0.5 FCKBD divided by FY 1 minus under root 1 minus 4.6 mu upon FCK BD square. So put the value, let me know the answer. I will tell you the value, just put those values. FCK is equal to 20, then B is equal to 1000, D is equal to how much it is? 170, then FY 415, and last thing is MU. You see for flight A, B and CD, what was the MU? It is around 39.31 kilonewton meter. We just put all these values. What is the answer? 700.70. So area of steel is 700.70 mm square. So what bar diameter we have assumed? 10 mm bar. So let us see how many number of bars are required. Calculate the number of bars. Now see, if we assume 10 mm bar diameter, then I am thinking that the number of bars are too much for 4 meter width. Okay, so instead of going for 10 mm bar diameter, take 16 mm bar diameter and see how many number of bars are required. Those are sufficient or not? If we take 16 mm instead of 10 mm, let me know. And if we take 10 mm bar diameters, how much bars are required? That okay. So it's okay. Take 10 mm bar diameter, no problem. So number of bars is equal to 700.70 divided by 5 by 4 into 10 square. So let me know 92. Okay, it is 8.92, which we will round to 9 numbers. 9 numbers. So AST provided now. What AST you are going to provide? AST provided is equal to 9 into 5 by 4 into 10 square. 706.85. 706.85 mm square. This is the area of steel we are going to provide. Now calculate the spacing. Now next point is spacing. Okay. So spacing of bars. Spacing of bars. So in this first spacing, as it can be calculated as area of single bar, area of single bar divided by AST provided, that is 706.85, multiplied by width, that is 1000, 111.11 mm. So we will round up this to 110 mm center to center. Again, what is the spacing? Second case, spacing is equal, yes, is equal to how much? It is 3D. So now 3 into D, calculate the answer. Let me know the answer. 3 into D. D is the effective depth. What was our effective depth? 3 into, I think it is 170. So it is 510 mm center to center. And in third case, in no case, spacing S is equal to how much it is? 300 mm center to center. So we are going to choose the minimum value from all these, and the minimum value is 110. So here I will write provide provide 10 mm diameter bars, 10 mm dia bars about 110 mm center to center. Okay, this is for flight AB and CD. This is for flight AB and CD. Now similarly, we will calculate the steel required for flight BC. Okay, so now steel reinforcement, steel reinforcement for flight BC. Again, AST is equal to, what is the formula? 0.5 FCK BD whole divided by Fy in bracket 1 minus under root 1 minus 4.6 mu upon FCK BD square. So again put the values. Okay. So here the bending moment is 36 point something, no, for flight BC. Put that value of bending moment for flight BC. Put the corresponding value of bending moment. 36 point something was the bending moment, I think so. So take that value over here and calculate the AST. Okay. It is 651.50 mm square. Okay. Now again calculate the number of bars. Number of bars. Assume same diameter 10 mm. So it is 651.50 divided by 5 by 4 into 10 square. So the number of bars are 8.29. So again, which is round up to 9 numbers. So number of bars are 9. So calculate AST provided now. Here AST provided is equal to 9 into 5 by 4 into 10 square. So how much it is? 706.85. So same 706.85 mm square. Okay. Now again calculate the spacing for each case. So for first case, spacing is equal to area of single bar divided by AST provided multiplied by 1000. This is how much. Then second thing, spacing S is equal to 3D, 3 into 170, so, sorry, 510, 10. What was the spacing for first case? It is, finally we round it up to 110 mm, I think. Center to center, this is center to center, and in no case spacing S is equal to how much it is? 300 mm center to center. Okay, so again you can write here provide 10 mm bar about 110 mm center to center. Okay, now after this main reinforcement we will go for distribution steel. Distribution steel. So for distribution steel, that is ASTD is equal to 0.12 divided by 100 into B into D, which is equal to 0.12 into 100 divided by 100 into B, 1000 into capital D is 190 overall depth. So if you solve, you will get the answer. 28 is 228 mm square. Okay. So now provide 8 mm bar diameter. So we will provide 8 mm. Assume 8 mm dia bars. Okay. So number of bars is equal to 228 divided by area of single bar, 4.53. 4.53 means we will clearly round up this to 5. So now ASTD provided, distribution steel provided. How much we have provided now? It is 5 into 5 by 4 into 8 square. Okay. 251.32. 251.32 mm square. This is the ASTD provided. Now calculate the spacing of distribution steel. So this part, spacing of distribution steel, we will take in the next lecture.